Hi everyone, welcome to our online class on electricity and electronics at Paradise Business and Technology College online classroom. I am Mr. John Kaupa, the class coordinator for the course. In this video, we are going to discuss Unit 2, which is Fundamental of Electricity and Electronics Circuits. Okay, our first topic in this unit is atoms. Atom is a basic building block of matter. Anything around us, even us, elements, they are all made up of atoms because they are matter. Matter, the tiny building block of matter is atom. In a study of electricity, we are going to start with atom because electricity is produced and is used from the atomic level. So it's good that we are going to understand how electricity is produced at the atomic level of conductors. Now, first of all, let's dive into it and see what is a atom. All matter is made up of atoms, and all atoms consist of electrons, protons, and neutrons. So atoms are the tiny building block, and they are made up of subatomic particles, which are called electrons, protons, and neutrons, which are present in the atom. The configuration of certain electrons in an atom is the key factor in determining how well a conductive or semiconductive material conducts electric current. So the arrangement of these subatomic particles, the protons, neutrons, and electrons in the atomic level determines the conductivity and performance of the different materials in the study of electricity. So it's very important that you understand what is an atom, what are the subatomic particles, and how do they contribute to the production of electricity at the atomic level in the conductive material. Okay, as you see from the diagram here, you will see that the nucleus is the center of an atom. When you take an atom of an element or of a matter, when you look at the center of that atom, there is a nucleus, which is the center of the atom. Surrounding the nucleus, you have cells, okay, cells or orbits. Okay, these subatomic particles occupy these positions in the atom, the cell, the nucleus, and all this. So now let us see what particle is present in the nucleus and what particle is orbiting the cell. So basically, you will know that the protons and the neutrons are present in the nucleus, okay, and electrons, they orbit the cell of the nucleus. So from our diagram here, you will see these rings here, they are the cells or orbits, where electrons is circulating around the nucleus of the atom, and in the nucleus we have the protons, okay. And these subatomic particles, they also have charges, negative and positive charge. So electrons, they have a negative charge, whereas protons, they have a positive charge. Neutrons, they don't have a charge, they are chargeless subatomic particles. Again, neutrons and protons are present in the nucleus, and electrons orbit the cell of the atom. Okay, when you talk about atoms, atomic number is a very important thing to discuss. All elements, they are made up of atoms, and they have atomic number. And how do you find this atomic number? You simply go to the periodic table, because in the periodic table, all the elements are arranged in the order of their increasing atomic number. From that atomic number, you will work out the number of protons, electrons, and neutrons which are present in one atom of that element. Okay, so all elements are arranged in the periodic table of the elements in order according to their atomic number. The atomic number equals the number of protons in the nucleus. So for example, for hydrogen, if it is atomic number 1, that means it has 1 proton in the nucleus. And if that hydrogen is stable and neutral, then the number of protons is equal to the number of electrons as well. So one proton, one electron, and one neutron. We also have helium as an atomic number of 2, which means to say that 2 protons in the nucleus, and because it's a stable and neutral helium atom, then the number of protons, neutrons, and electrons are equal. Unless if the atom is not stable, if it is a isotope, or if it is a ion, anion, or cation, then the number of protons, neutrons, and electrons are not the same. They are quite different in number. Okay, let's take carbon as an example. When you look at carbon in the periodic table, there are 2 sets of numbers at the back of carbon, C, 12 and 6. 12 is the mass number and 6 is the atomic number. Mass number is always greater than the atomic number. Mass number equals to the number of protons plus the neutrons, and atomic number tells you the number of protons. So when you subtract the protons, the atomic number, from the mass number, you will come up with the number of neutrons, because mass number is equals to the number of protons plus the number of neutrons. Okay, that's for stable atoms of all the elements. They have equal number of protons, neutrons, and electrons. But if they display some property of isotopy, or if we have isotopes of some atom, okay, that's when they will have different number of neutrons, protons, and also if the atom give or receive electron, that's when they become ion, or whether a cation or a anion. So that's when the number of electrons, protons, neutrons are not equal. Like for instance, for carbon as an isotope of carbon-13 and carbon-14, when you work out the number of protons and neutrons, they are not equal. And when you look at the ion, like sodium ion and all this, okay, they donate electron, so you'll see that the number of electrons in this atom is not the same as the protons and the neutrons. Only when the atom is stable and neutral, that's when the number of protons, neutrons, and electrons are equal. Okay, these protons and neutrons, they are present in the nucleus of an atom, while electrons, they orbit the cell of the atom. So electrons, cells, and orbits, okay, they are the circular rings around the nucleus or core of the atom. Electron orbit the nucleus of an atom at certain distances from the nucleus. Electrons near the nucleus have less energy than those in more distant orbits. The electrons which are closer to the nucleus, because in an electronic configuration of an atom, you will see that there are rings, or there are cells that surrounds the nucleus, and we don't have only one, but there are certain number of them depending on different types of atom. But the one that is closer, the cell that is closer to the nucleus, has a maximum of 2 electrons, and the second cell will have a maximum of 8, the third will have a maximum of 16, the fourth will have a maximum of 32. And okay, as you have the number of cells increasing, you will see that the number of electrons occupying each cell will increase. Okay, so there's a rule and formula there, but the point is the electrons that are closer, orbiting the inner cell, closer to the nucleus, have less energy, because less energy in the sense that they can't be released or moved easily, because they are attracted to the protons in the nucleus or core of the atom. Because according to the Coulomb's law, it states that, okay, the greater the distance between two charged particles, the lesser the electrostatic force that exists between them. The smaller the distance between, the closer the charged particles, the greater the electrostatic force. So that applies here. Electrons is a negative charge and protons is a positive charge. So like charges, they repel, and unlike charges, they attract. So protons and neutrons, electrons, they tend to attract to each other. So that's when the electrons closer to the nucleus of the atom have less energy to move. Okay, valence electrons that are in orbit further from the nucleus have higher energy and are held less tightly around to the atom than those closer to the nucleus. This atom or cell is known as the valence cell, and electron in this cell are called valence electrons. So as you go further from the core of the nucleus, we have a chopper flying over my house. Okay, as you go further from the nucleus of the atom, you will see that the number of electrons occupying the feather cell will have more energy to freely move, because the force of attraction between the protons and that electron in the outer cell is less. So that electron in the outer cell, it's called a free electrons. It's ready to move, or sometimes they involve in chemical reaction. That's why they say valence electrons. The outermost cell that holds the valence electrons is called a valence cell. Okay, let's discuss about how to work out the number of protons, neutrons, and electrons in an atom. To determine the number of protons, neutrons, and electrons for any element, use the periodic table and the following rules. How do you use the periodic table? You identify the element. You record the two numbers, the mass number and the atomic number. Mass number is always greater than the atomic number. Like for carbon, it's 12 and 6. 6 is the atomic number, which is less than 12. 12 is the mass number. The number of protons is always equals to the number of the atomic number, or in other words, the atomic number is always equals to the number of protons. Electrons, the number of electrons is equal to the number of protons in a neutral atom. When an atom is neutral and stable, that's when the number of protons and electrons are equal. Okay, like in the previous slide, for stable carbon-12 atom, the number of protons is 6 and the number of electrons is 6. If an atom is an ion, when it loses electron or when it gains electrons, it becomes an ion. Subtract the charge from the number of protons. Okay, neutrons, the number of neutrons is calculated by subtracting the atomic number from the mass number, because the mass number is equals to the number of protons plus the number of neutrons. These subatomic particles, they also have charges and mass. Protons have positive 1 charge. Neutrons does not have a charge, is a chargeless subatomic particle. Electrons has a -1 charge, and protons and neutrons have 1 AMU, or atomic unit mass, or atomic mass unit, sorry. And then electron, the mass is not really zero, practically zero, but it's very small. But here it's saying 0. Okay, protons and neutrons are present in the nucleus, and electrons orbit the cell of the. Okay, this is a modern periodic table. A basic definition of a periodic table is it is an arrangement of all the elements in the order of increasing atomic number, and also it is arranged based on their physical and chemical property as well. But one of the nature in which these elements are arranged is they are arranged according to their increasing atomic number. Like for instance, let's take hydrogen. Hydrogen is 1 from the top left. When you go across top right, you will see helium, that's 2. Okay, when you right under hydrogen, you will see lithium and beryllium, that's 3 and 4. When you come across, there's boron, carbon, nitrogen, 6, 5, 6, 7, 8. So increasing, they are arranged in an increasing order of atomic number, apart from other nature that they are characterized in, like in terms of their chemical and physical property. Elements arrangement in a periodic table is in an order of increasing atomic. Okay, let's take carbon as an example. Carbon is an element, but it is made up of number of atoms. When you take one atom of carbon, there are a certain number of neutrons, protons, and electrons present in that one atom of carbon. So how do we work out this number of protons, electrons, and neutrons? The key is we go back to the periodic table, we find out the mass number and the atomic number of carbon, which is already given here. C is the symbol of carbon, and you see two sets of numbers, 12 and 6 at the back of C. 12 is the mass number, which is equals to the sum of protons and neutrons, and 6 is the atomic number, which is also equals to the number of protons present in the nucleus of a single carbon atom. For a neutral and stable atom of every element, the number of protons, neutrons, and electrons is the same and equal, unless it's a ion, that atom becomes an ion, or it is isotopes, like carbon has isotopes like carbon 13 and carbon 14, where the mass number is different. So when you work out the number of protons and the neutrons, they are not quite the same and equal. Okay, for atoms, okay, that becomes ion, okay, by losing or gaining electrons, will not have the same number of electrons and protons, because they have already donated some electrons, or they have already accepted some electrons. Okay, let's look at chlorine atom here. Chlorine is an atom of chlorine element, or chlorine element. When that one atom of chlorine gains electrons, it becomes a anion. Okay, all atoms that gains electron are anion, negatively charged ion. They become an ion, but negatively charged ion. All elements that donates or loses electrons becomes a positively charged ion. Okay, so basically when an atom of an element loses or gain electron, it becomes an ion. When it loses, it becomes a positively charged or cation. When it gains, it becomes a negatively charged or anion. So chlorine atom of chlorine element, when it loses, when it gains electrons, it becomes a chlorine ion, and sodium atom of a sodium element becomes an cation when it donates electrons, or sodium ion. So that's when the number of protons and the neutrons are, and the electrons as well, they are not equal, because that atom is already unstable when it loses electrons or gain electrons, and it's no longer neutral or stable. Okay, in the study of electricity, we have three categories of materials here. In terms of electrical conductivity, we have conductor, insulator, and semiconductor. In basic understanding, we say conductor conducts electricity, insulator does not conduct electricity, semiconductor acts in between a conductor and insulator. Sometimes it becomes a conductor, sometimes it becomes a insulator. But we can also classify these materials based on their atomic structure and electronic configuration, or in other words, their atomic structure and electronic configuration constitutes their ability or their property of electrical conductivity. Like for conductors, mostly metals, you will see their valence shell will hold 1 to 3 electrons, or valence electrons. Insulator, their valence shell is full, mostly non-metals. Semiconductors, we have 4 valence electrons, like germanium, silicon. These are semiconductors. Okay, let's look at the three different types of materials: conductors, insulators, and semiconductors. Conductors, basically they allow current to flow through, or they conduct electricity. When you look at the atomic structure, there are 1 to 3 valence electrons in the valence shell. Mostly they are metals, copper, silver. They are good conductors. They are used for electrical wires and all this. Semiconductors, sometimes they behave as conductors, sometimes they don't. When you look at the atomic structure, there are 4 valence electrons. Examples are germanium and silicon and all this. Because of their properties, that they sometimes they don't conduct electricity, they are used in electronics, like transistor and diodes and all this. Insulators, they do not conduct electricity. They don't have any valence electrons, free electrons. Their orbit or their cell is full. Okay. Examples of insulators are mostly non-metals. They are used for insulation and protection, like insulation of wires and all this, just to protect the flow of electricity. So these are the different. Okay, let's look at copper. Copper is a very good conductor. Why is it a very good conductor? Let's look at the atomic structure of copper. Like I said earlier on, the conductivity of a material depends on its electronic configuration. So copper is a good conductor because when you look at the electronic configuration of copper, there's a lot of electrons in there. There is one valence electron in the outermost cell. So when the voltage is applied, that electrons move, and then you see that other electrons in there as well. There are free electrons, a lot of free electrons in the atomic structure of copper. So that makes copper a good conductor. Copper is the most commonly used metal in electrical applications. The copper atom has 29 electrons that orbit the nucleus in 4 different cells. So like I said, the rule of distribution of electrons among the cells: the first cell will hold a maximum of 2, the second will hold a maximum of 8, the third will hold a maximum of 16 electrons. So and then the fourth will hold a maximum of 64 electrons. Okay, so when you look at copper alone, because it is a lot of electrons in its atom, that's when it makes it becomes a good conductor. So not only copper but other good conductors as well. You will see a lot of electrons in their electronic configuration in the atomic level. That's when they make up a good conductor. So when you minus the mass of copper when its atomic number, you will see that it has 229 electrons. When you divide it among the 4 cells, 2, 8, 16, 1, so that adds up to 29 electrons. So only 1 valence electrons. The inner cell gets 2, and then we have 29 protons and neutrons present in the nucleus or core of the copper atom. Okay, our next topic is electrical charge. When you look at electricity, we are talking about current, and current is basically a flow of charge. When a group of charge move past across a point in time, that's when we have a current, flow of current. Okay, and if the material in which that the group of charges passes through resists the flow of that group of electrons, that's when we have resistance. The forces that pushes this group of electrons within that conductor across over a point of time is called a voltage. So there is work done to move these electrons across. So basically electricity is it's the movement of charge, electrons, that causes current. Okay, so as you know, an electron is the smallest particle that exhibits negative electrical charge. When an excess of electron exists in a metal, there is a net negative electrical charge. When a deficiency of electron exists, there is a net positively charged. So that it refers to the ion and anion and cation. When there is a deficiency, meaning minus anion. When there is a excessive electron, that's plus, meaning positive or positively charged ion. Okay, when you talk about charges, there are like charges and unlike charges, positive and negatively charged particles. Okay, electron is a negatively charged particle, proton is a positively charged particle. So they attract to each other when they are opposite charges, they repel when they are like charges. So electrons and protons, they are opposite charges, so that's why they attract to each other. Okay, when there is a attraction, there is a force of attraction between the unlike charges. When there is a repulsion, there is a repulsive force between like charges. So this force can be calculated using the Coulomb's law. Electrostatic force is equals to a Coulomb constant times Q1 and Q2 divided by the square root of the distance that separates the two charges. Okay, so okay, that brings us to Coulomb's law. Coulomb's law states that a force exists between 2 point source charges Q1 and Q2 that is directly proportional to the product of two charges and is inversely proportional to the square root of the distance between the charges. So this is Coulomb's law there. F is the force, electrostatic force between the two charges, is equals to K, which is a Coulomb's constant, charge 1 times charge 2 over the square of the distance between the two charges. So that force here, it can be a repulsive force when two like charges come together, and it can be a attractive force when two unlike charges come together. Okay, the unit of coulomb. Electrical charge is measured in coulomb, symbolized by C. 1 coulomb is the total charge passed by 6.25 times 10 raised to 18 electrons. Okay, a single electron has a charge of 1.6 times 10 raised to 19 coulombs. The total charge Q expressed in coulomb for a given number of electrons is found by the following formula. Q is equals to N times E, where Q is the total charge, N is the number of electrons or protons, E is equals to charge of electrons or protons. Okay, the unit of electrical charge is coulomb. Let's see why is it named as coulomb. Charles Augustin Coulomb was born in 1736 and he passed on in 1806. He's a Frenchman. He spent a lot of years as a military engineer. When bad health forced him to retire, he devoted his time to scientific research. He is best known for his work on electricity and magnetism due to his development of the inverse square law for the force between two charges. So in other words, that's the Coulomb's law. The unit of electrical charge is named in his honor. So because of his dedication and work in the field of electricity and magnetism, the unit of charge, electrical charge, is named in his honor. Okay, let's look at one example here. How many coulombs of charge do 93.8 times 10 raised to 16 electrons represents? Okay, so when we rearrange the formula, we will have Q charge is equal to number of electrons divided by number of electrons per charge. So for one charge, we have 6.25 times 10 raised to 18 electrons for one coulomb. Okay, so in one coulomb of charge, there are 6.25 times 10 raised to 18 electrons present in one coulomb of charge. So how many are present in how many coulomb of charge are present in 93.8 times 10 raised to 16 electrons? Okay, so when you do a division there, we will end up with 15 times 10 raised to negative 2 coulombs. So which means you say that in 15 times 10 raised to negative 2 coulomb, we have 93.8 times 10 raised to 6 electrons present, okay, or 0.15 coulombs. You can study this example here and refer to the formula then try to make sense of it. Okay, now let's look at voltage. As you have learned, a force of attraction exists between a positive and a negative charge. A certain amount of energy must be exerted in the form of work to overcome the force and move the charge a given distance apart. All opposite charges possess a certain potential energy because of the separation between them. The difference in potential energy of the charges is the potential difference of voltage. Voltage is the driving force in electric circuit and is what establishes current. Voltage is defined as energy per unit of charge and is expressed as V is equals to work on charge, or you can say electrical energy divided by charge, or in Ohm's law we say current times resistance. Voltage, to put it in simple terms, it's a force that pushes the electrons. Electrons are particles already present in the atom of the material or the conductor. When voltage is applied, there is a force that pushes these electrons to the conductor. When these electrons move in the conductor, there is current and electricity. So sometimes they say electromotive force or EMF or potential difference. This is the same thing. EMF means electron, motive, motion, and force means force. It's a push. Okay, so basically voltage is a force. So when people are electrocuted, it's not the current that kills them, it's the voltage that kills them because it's a force. Okay, let's look at the unit of voltage. Alessandro Volta was born in 1745 and died in 1827. He's an Italian by nationality. He invented a device to generate static electricity and he discovered methane gas Volta investigated reaction between dissimilar metal and developed the first battery in 1800. Electrical potential or voltage, more commonly known as voltage, and the unit of voltage, the volts are named in his honor. So that's him there. Okay, the unit of voltage is volts, symbolized by V. 1 volt is the potential difference between 2 points when 1 joule of energy is used to move 1 coulomb of charge from one point to another. Okay, so this is the relationship between voltage, energy, and charge and electrons. So when there is a movement of charge, then there's a group of electrons moving under the influence of force, and that force is the voltage. So let's see an example here. If 50 joule of energy are required to move 10 coulomb of charge, in that 10 coulomb of charge there's a group of electrons moving, which are electrons. What is the voltage? So when you look at when you use the voltage and work charge relationship, V is equals to energy or work done to move the charge divided by the charge. So 50 divided by 10 is 5 volts. Okay, so basically electrons are particles. In order to move them, we need force. Newton's second law of motion, force is equals to mass times acceleration. We need force to accelerate an object. So electrons are actually particles because they have mass. In order to move them in the conductor, they need to be a force, and that force is voltage. Okay, voltage sources. Voltage sources can be DC or AC voltage. DC voltage can be batteries or solar panels. These are DC voltage sources. AC, we can have generator. I can produce AC sources. Below are some of the common types of batteries for DC sources: alkaline batteries, carbon batteries, and then we have lead acid batteries. Okay, so these are the different types of batteries that we have. We have lithium ion. This is a secondary battery that is commonly used in all types of portable electronics. This type of battery is increasingly being used in defense, aerospace, and automotive appliances. Lithium ion. Lithium magnesium oxide. This is a primary battery that is commonly used in photographic and electronic equipment, smoke alarms, personal organizers, memory backups, and communication equipment. Nickel metal hydride. This is a common secondary rechargeable battery that is commonly used in portable computers, cell phones, camcorders, and other portable consumer electronics. We also have silver oxide. This is a primary battery that is commonly used in watches, photographic equipment, hearing aids, and electronics requiring high capacity battery. We have zinc here. This is a battery that is commonly used in hearing aids like headphone and all this, medical monitoring instruments, and other frequency use appliances. So these are some of the different batteries that we have, battery sources. Okay, now let's look at current. Voltage provides energy to electrons that allows them to move through a circuit. This movement of electrons is the current. When voltage pushes the electrons, when the electrons move in the conductor, then we have current, which result in work being done in an electric circuit. So when there is a force applied to move an object or particle over a distance, then work is done. So that work, in the perspective of electrical, we say work done to move the electrons. Okay, work done by the voltage. So that's how we understand electricity. These electrons are readily available in the conductor. Okay, we just need the voltage to push them through the conductor. When they move, there is current. Okay, when we talk about movement of charges or electrons in a circuit, in a closed path, And of course, when there is a closed path, there is a flow of current. If there is an open circuit, current doesn't flow. There are two types of current flow: convectional current and the actual current flow. Okay, the current flow or movement of electrons or flow of electrons is always from negative, out of negative terminal, come back to positive. That's a flow of the current or electrons. The convectional current is the opposite flow of electrons. Okay, convectional current is from positive to negative. Okay, so these are the two different types of flow of current. Negative to positive is the flow of electrons or current. Positive to negative is convectional current. Okay, the movement of the free electrons from the negative end of a material to the positive end is the current, electrical current, symbolized by I. Electrical current is the rate of flow of charge, and convectional current is the opposite, from positive to negative. Current in a conductive material is measured by the number of electrons, amount of charge that flow past the point in unit of time. So another thing is we have two types of voltage sources, also two types of current sources. AC current, the current changes direction periodically, so that's why we say AC, alternating current. DC, only in one direction, negative to positive, negative to positive. Okay, and then the convectional current is from positive to negative. So this is the difference between AC and DC. DC does not have frequency, AC has frequency because of its alternating nature. Okay, the unit of current. Current is measured in a unit called the ampere or amp for short, symbolized by A. 1 amp is the amount of current that exists when a number of electrons having a total charge of 1 coulomb move through a given cross-sectional area in 1 second. So current is equal to charge divided by time. Okay, or in Ohm's law we say voltage divided by resistance. Okay, when we talk about electrical current, is the flow of charge under the influence of voltage. It's a physical quantity, and the unit is ampere or amps. Where does this ampere come from? In fact, that ampere is the name of a person who is a Frenchman. His name is Henry Marie Ampere. He was born in the year 1775 and he passed on in 1836. Okay, in the year 1820, he developed a theory of electricity and magnetism that was fundamental for 19th century developments in the field of electricity and magnetism. He was the first to build an instrument to measure charge flow, which is flow of current. The unit of electrical current is named in his honor. So that's Henry Marie Ampere there. Okay, this is an example here. 10 coulomb of charge flow past a given point in a wire in 2 seconds. What is the current in the circuit or in the wire? Okay, current is equal to charge on time. 10 coulombs divided by 2 seconds is equals to 5 amps. Okay, now let's look at resistance. When the electrons are pushed by the voltage through the conductor, then there is a resistance. Okay, resistance through the material that pushes the electrons back. That's resistance of the material. Okay, when there is current through a material, the free electrons move through the material and occasionally collide with atoms. These collisions cause the electrons to lose some of their energy, and thus their movement is restricted. The more collision, the more the flow of electrons is restricted. This restriction varies and is determined by the type of material. The property of a material that restricts the flow of current is called the resistance and is designated by R. Okay, let's look at the unit of resistance. Resistance is R. The symbol of resistance is R, is expressed in the unit of ohms, which is symbolized by the Greek letter omega, which means to say that 1 omega or 1 ohm of resistance exists when there is a 1 ampere of current in a material with 1 volt applied across the material. Okay, conductance is also one of the property of a material with regards to its conductivity, and it's the inverse of resistance. The inverse of resistance or reciprocal of resistance is the conductance, symbolized by G. It is a measure of the haze with which current is established. The formula is G, inductance is equals to 1 on resistance. So to put it in simple terms, the greater the resistance of a material, the less conductive it is to electrical current or electricity. The lesser the lower or the lesser the resistance of a material, the greater the conductivity or conductance of that material. Okay, so that's what it means. So the unit of conductance is Siemens. It's measured in Siemens. The unit of conductance is in Siemens, symbolized by S. For example, the conductance of a 22 kilo ohm resistor is 1 on 22 is equals to 45.5 micro Siemens. Okay, so basically conductance is the inverse of resistance. Resistance is the inverse of conductance. The higher the conductance, the lower the resistance. The lower the resistance, the higher the conductance. The unit of resistance. George Ohm was born in Bavaria and struggled for years to gain recognition for his work in formulating the relationship of current, voltage, and resistance. This mathematical relationship is known today as the Ohm's law, and the unit of resistance is named in his honor. So that's George Ohm there. Okay, now let's look at resistors. What are resistors? What's the difference between resistors and resistance? Resistance is a internal property of a conductor. Resistors are the components that are made. Okay, so resistance is the property of a material in which current is flowing through, and resistors are constructed for the reason to control current and voltage in a second. So components that are specifically designed to have a certain amount of resistance are called resistors. The principal application of resistors are to limit current, divide voltage, and in certain cases generate heat. Although different types of resistors come in many shapes and sizes, they can all be placed in one or two main categories: fixed or variable. So we have variable resistor, meaning you can vary the value of the resistor, increase or decrease to control the current and voltage, or fixed value, you cannot change that. These are some of the examples of resistor. We have carbon composition resistor, metal film chip resistor array, we have resistor network, we have resistor. Okay, these are different types of resistors here. Okay, among all the fixed resistors, one of the commonly used resistor is the carbon composition or carbon film resistor. It is like a parrot. Why I'm saying parrot? Because it has color codes on it like the color of the parrots. So that's why when I want to explain it to my students, I used to refer them to as parrots on the circuit boards because of all sorts of colors on them. But these colors gives you a clue to use and work out the value of these resistors. So you will see on the resistor there are different colors, so we call them different bands of colors. Like for this one here, we have a 5-band resistor here. So basically, when you start from the left, you will see the first digit, and then the second band is the second digit, the third band is the third digit, the fourth band is the multiplier, and the last is the tolerance. Okay, how do you work out this value? We have a table of colors on the other side, the green table there. You see all the digit and the color on the other side. You look at the color, you get the digit, you put them together, and then you can work out the value. So for this case here, the first digit is gray, so it's 8. The second digit is red, so it's 2. So 8, 2. The third digit is orange, that's 3, so 8, 2, 3. And the fourth digit is the multiplier, which is yellow. Yellow is 4, so 8, 2, 3 times 10 raised to 4. Why 4? Because yellow is 4, multiplier which is 10 raised to 4, or 4 zeros. Okay, and then the tolerance is red, which is plus or minus 2%. Tolerance is down there below the table, green table there. So that's how you use the color codes to work out the value. After you work out the value of the resistor from the color, you can actually get the multimeter or ohmmeter to measure the resistance of the resistor and confirm it with your manual calculated values. Find the resistance value in ohm and the percent tolerance of each of the color coded resistor here. The first band, look at A here, we have first band is red, that's 2 from the table. Second band is violet, that's 7 from the table. Third band is black, it's 0 from the table. Fourth band is the multiplier, okay, it's times 10 raised to negative 1. Fifth band is red, it's the tolerance, plus or minus 2%. So the value of the resistor, depending on the color code, is 2 for red, 7 for violet, 0 for black, and yellow is the multiplier times 0.1, and then you will have 27 ohm plus or minus 2%. So that's how you work out the resistor. So when you take the measurement of that, it must range between plus or minus 2%. So because there is error in measurement, so when you make an error, then that 2% is tolerance, or it's called a correctional factor. Okay, but if you have any question, you can always raise it. But you can look at the second example and third example. The numbers here are taken from the color here, so you can just associate with numbers with the color and go back to the previous slide and look at the table. That's how you work out the value of fixed resistor from color. We also have labels and resistor that you can calculate value. Resistor label codes, okay, not all types of resistors are color coded. They have some alphanumeric codes on it, so you can also use that alphanumeric coding. Like for this case, first digit is 1, second digit is 2, third digit is 3, which is the multiplier. So 1, 2, 3, that means 12 times 3 is 10 raised to 3, so that's 12,000 ohms or 12 kilo ohms. Okay, there are some other examples here. In some cases we have letters, so that's why there's alphanumeric coding. Some resistors don't necessarily have colors, but they have codes, mixture of numbers and letters. Okay, so the letter R, M, K, and all this. So these are some examples there. You can just look at it, and then if you have question, always come back to me. Okay, when we talk about resistors, there are basically two types of resistor. One is a fixed resistor. Fixed resistor as a fixed resistance or fixed ohmic value, like carbon composition, or as color codes on them. Variable resistors are resistors that has a value that can be altered or changed, or varying value of resistance. Okay, one of the application of variable resistor, they are used in tuning circuits. Not only variable resistor, but variable capacitor and inductors are also used in tuning circuits. Okay, variable resistors are designed so that their resistance value can be changed easily. Two basic uses for variable resistor are to divide voltage and current, and to control current in a circuit. The variable resistor used to divide voltage is called a potentiometer. The variable resistor used to control current is called a rheostat. Okay, so the symbol of a variable resistor is down there, a resistor, and an arrow crossing the symbol of resistor is a variable resistor. Okay, now let's look at the electric circuit. A basic electric circuit is an arrangement of physical components that uses voltage, current, and resistance to perform some useful function. So this is a basic electrical circuit. We must have a load, we must have a source of power, and we must have a conductive path where the current will flow from the source to the load. Okay. When we talk about electric circuits, mostly we don't draw circuits in the artistically, but they use symbol. So these are some of the symbols that they use: resistor, ammeter, voltmeter, okay, motor, inductor is a coil of wire, switch, lamp, capacitor, transformer, ground, DC voltage, and diode. These are some of the examples of some of the symbols, common symbols used in circuit diagrams and schematics. The reason why I put a lot of symbols here is because in some texts they use other symbols. It's the same component or same thing, but they're using other symbols. Resistor, variable resistor there, you see, this is a sign of a variable resistor. Up there is a fixed resistor. And then you have other symbols here. You can just read this one and make sure you draw them down and understand them. We have other symbols here, circuit symbols: battery, resistor, potentiometer, rheostat, lamp, ground, and then switch. So these are the basic components of a circuit: switch, a load, and battery or power source, and all these things here. And then if you are trying to use some instrument to perform basic measurements of current, voltage, or whatever, then these are the symbols there that you know that there is a instrument inserted into the circuit to do measurements of current, voltage, or resistance. We also have fuse and circuit breaker here. Okay, these are protective devices to protect the circuit and also to control current in the current voltage in the circuit. Okay, circuit current control and protection. The figure illustrates a closed circuit and an open circuit. We have two types of circuit. An open circuit is when there is a discontinuity somewhere, so current does not flow. Current does not flow through an open circuit. We have a closed circuit. That's when we have switch coming into play. Switch is a control device that open and close the circuit for current to flow through from the source to the load. So these are the basic components of a basic circuit: power source, conductive material part, usually is a wire conductor. We have the switch, load, and of course for every circuit, for safety reason, there must be ground present. Switch can be electromechanical switch or mechanical switch. Relay is an electromechanical switch. Push button is a mechanical switch. So mechanical switches are commonly used for controlling the opening or closing of circuits. We have different types of switch here: double pole, single throw, DPST, double pole, double throw switch, push button, and rotary. A rotary switch, something similar to your fan knob. Okay, push button, anything that you push on and off. Okay, so these are push button, and the symbols are here. You can just draw these symbols down and be familiar with them. SPST, single pole, single throw. SPDT, single pole, double throw. DPST, double pole, single throw. DPDT, double pole, double throw. NOPB, normally open push button. NCPB, normally closed push button, and single pole rotary switch, so like similar to the one for fan regulator. This is also a switch, mechanical switch, control switch. The function of switch is to open and close the circuit or control the flow of current in the circuit. Circuit protective device, we have fuse and circuit breakers. They protect the circuit in the event that if there is overcurrent flowing through the circuit, then they protect the circuit, especially the load and the circuit from catching fire and all this. So fuse and circuit breakers are placed in the current path and are used to deliberately create an open circuit when the current exceeds a specific or specified number of amperes or current to malfunction or other abnormal conditions in a circuit. Okay, wires. What are wires? Wires are very important components of a circuit because they provide a pathway for electricity to flow through in a circuit, and also, in fact, they contain the electrons. These electrons that moves, and when they move, they become current. They are present in the wires. Okay, so when we apply voltage, the voltage pulls the electrons through the wires. So wires are the most common form of conducting materials used in electrical application. They vary in diameter, size, and are arranged according to standard wire gauge number called AWG, American wire gauge, or AWG sizes. So basically, as the gauge number increases, the wire diameter decreases. So the greater the AWG number, the smaller the diameter, or the smaller the wire. The smaller the AWG number, the greater the size of the wire. So that applies to any cable or any cable TV or power cables or whatever it is. They all of them have a AWG number. The greater the AWG number, the smaller the wire size. The smaller the AWG number, the greater the wire size. Okay, the next thing is resistance, wire resistance. Any material that allows electricity to flow through must have a value of resistance. If it does not, then the current does not flow through. In two conditions, electricity does not flow in a material is when they don't have a resistance, or when the material has an infinite resistance value. That's when current does not establish in that type of material. Although copper wire conducts current extremely well, it still has a value of resistance or some form of resistance, as all conductors do, or as do all conductors have resistance value. The resistance of a wire depends on three physical characteristics: the type of material, or the element that made up the material, length of the wire, and the cross-sectional area. And in addition, temperature can also affect the resistance. So temperature is sometimes affects the resistance value. So generally, temperature increases with resistance. Okay, and the higher the temperature, the higher the resistance. The lower the temperature, the lower the resistance of a material. Okay, there is a formula that is used to calculate the resistance of a conductive material, which is R is equals to rho, which is the resistivity of the material, times the length of the material divided by the cross-sectional area of the material. This formula is very useful especially for electrical engineers when calculating the line loss of distribution lines. They use this formula to find out the resistance and calculate the amount of power loss on the line during the course of transmission. So that is a very important formula as well for the power system engineers, especially distribution lines loss. Okay, there is an example here. Find the resistance of a 100 feet length of copper wire with a cross-sectional area of 810.1 cm. The resistivity of copper is 10.37 centimeter ohm per feet at 20 degrees Celsius. Okay, so when you plug in the values there, you see the resistivity times the length divided by the cross-sectional area will give you 1.280 ohm, which is the resistance of the wire. Ground is the reference point in a circuit or electric circuit. The term ground originated from the fact that one conductor of a circuit was typically connected with an 8-foot long metal rod driven into the earth itself. So grounding is also a safety. Anything happens in a circuit, the fault current in a circuit quickly go through the ground and go down to the head. Comparing all the type of conductors, especially in electrical, ground conductor has the low resistance. So that's when in the case of fault, the current quickly go to the ground conductor and go to the earth for safety reason and all this. So you see that grounding symbol there. That means the circuit is grounded. You can ground the source, voltage source, You can also ground the load side of the circuit. Okay, so in a circuit, grounding is very important. That's for safety. Anything happen within the circuit, then the fault current goes to the ground. If there is no grounding, then the circuit is already unsafe. Okay, measurements of basic electrical quantities. Voltage, current, and resistance measurements are commonly required in electronics work. The instrument used to measure voltage is a voltmeter. The instrument used to measure current is an ammeter, and the instrument used to measure resistance is an ohmmeter. Commonly, all three instruments are combined in a single instrument known as multimeter, in which you can choose the specific quantity to measure by selecting the appropriate function with a switch. So multimeter performs resistance, voltage, and current, even capacitor, inductor, frequency, whatever it is, all multiple measurements. Again, instruments can be analog instruments or digital instruments used to measure all these parameters of seconds. Measuring current. When you want to measure current, the meter is inserted into the circuit. Okay, you connect the ammeter in series with the circuit to measure the current in the circuit. So you break open the circuit, put the meter in there, the ammeter in there, and then it will measure the current. And it's different from voltage voltage measurement. You connect the voltmeter in parallel with the component that you are trying to find out how many voltage drop at that component, like the resistor there. You see that resistor, the circuit diagram there. The voltmeter is connected in parallel with the resistor to measure voltage. For resistance measurements, it's similar to voltage measurement. You connect the ohmmeter in parallel with the resistor to measure the resistance. But one important tip is always disconnect the resistor from the circuit, so there is no power supply going through the resistor before doing measurements of its resistance. So voltage and resistance measurements, the meter must be connected in parallel, while only for current the meter becomes part of the circuit and is connected in series with the source. Okay, that brings us to the end of the unit, the summary to that unit. There's some points here. An atom is the smallest particle of an element that retains the characteristic of the element. The electron is the basic particle of negative electrical charge. The proton is the basic particle of positive charge. An ion is an atom that has gained or lost an electron and is no longer neutral. When electrons in the outer orbit of an atom, or which is a valence electron, break away, they become free electrons. Okay, and these free electrons make current possible. Like charges repel, and opposite charges they attract to each other. Like electrons and protons, they attract to each other. Electrons and electrons, or protons and protons, they repel. Voltage must be applied to a circuit before they can be current. Okay, without voltage there is no current. Summary continues. Resistance limits the current. Basically, an electric circuit consists of a source, which is a AC or DC source, a load, which is a AC or DC load, something or any equipment or any appliances that consume electricity, and a current part, which is the conductive material or conductor, like copper. An open circuit is one in which the current part is broken. Okay, a closed circuit is one in which has a complete current path. An ammeter is connected in line or in series with the current path to measure current. A voltmeter is connected across or in parallel with the current path to measure voltage. An ohmmeter is connected across a resistor to measure resistance. The resistor must be disconnected from the circuit. So basically, to measure the resistance of a resistor, you must not connect power supply to the resistor. Disconnect that resistor from the circuit and you can measure its resistance. One column is the charge on 6.25 times 10 raised to 18 electrons. 1 volt is the potential difference between 2 points when 1 joule of energy is used. to move one column of charge from one point to another. 1 ampere is the amount of current that exists when one column of charge moves through a given cross-sectional area of a material in 1 second. 1 ohm is the resistance when there is a 1 amp of current in a material with 1 volt applied across the material. That's all. Okay, thank you for your time. End of unit 2 presentation.